Topology. Topology is the branch of mathematics which studies shapes and equivalence by distortion. Okay, so what does that mean? You've probably never heard of topology before. In fact, usually people don't get a chance to take a course in topology until they're working on their PhD. So why are we doing it now? One reason is we can hit the high points and explain some of the interesting parts without having to go into an enormous amount of detail. Two shapes are equivalent by distortion. The technical term is homeomorphic, homeo meaning same and morphic being shape, if you can stretch one into the other without cutting or tearing it. So all these shapes are equivalent. The oval, rectangle, circle, and triangle could all be stretched one into the other without cutting it or tearing it. So you have to imagine that these are made out of special rubber topology material stuff so that you can take this ellipse, say, and stretch it and even crease it into a corner. That's okay, but you can't cut it or tear it. Well, all of these shapes are equivalent. Here's a square with an ellipse cut out. That's exactly the same as a circle with a rectangle cut out. Sort of looks like maybe the front end of the ship from 2001, or maybe the front of a Cylon helmet. Expect to see a little red light go to and fro across the cutout. But either way, those are the same. You can stretch the square into a circle, and you can stretch the hole, the elliptical hole, into a rectangular hole. The same with the diamond with a cross cut out. All those shapes are equivalent by distortion. You can stretch one into the other. But all of these shapes at the bottom are different. Here's an arrow. That shape is different from any of the others because in order to get one of the shapes above, you'd have to tear a hole in the middle. It's the same as a regular triangle or square that doesn't have a hole in it, but it's not the same as one that does. Here's a stop sign with two holes in it. In order to make that be like one of the shapes at the top, we would have to tear a hole in one of the shapes at the top or plug one of the holes at the bottom. Remember, if shapes are equivalent by distortion, we can't cut or tear them, so we can't create or get rid of a hole. Here's a smiley face. It has three holes inside. So again, it's different from the ones at the top and also the others at the bottom. Remember, we can stretch or shrink, but one thing we can't do is shrink a piece away to nothing. That would be cutting it and taking it away. For example, these one-dimensional shapes are equivalent. Notice that the figure on the left and the figure on the right are almost the same. The only thing that's happened is this extra line has been stretched around to the side. We haven't done anything cutting, or we haven't shrunk away anything to nothingness. So these two are perfectly equivalent to each other. On the other hand, these are not. The one that looks like a little space alien here at the bottom has two lines sticking out of it. In order to make it be the same as the ones at the top, we'd have to lose an antenna, and we can't do that and stay equivalent by distortion. We can't cut a piece, we can't shrink away a piece to nothingness. The middle figure here would be equivalent to the two at the top, but not to the space alien with two antennae on the left, because it only has one antenna. And of course, a circle with no antenna would be different from all three. Here's another way to see that the circle and the space alien with one antenna are not equivalent to each other. Notice that if you remove a point from the circle, it always leaves one connected piece. Suppose you took a circle and cut it in one place. You would have one piece left over. On the other hand, if you remove this red point from the space alien with one antenna, what happens? If we remove that particular point, we have two disconnected pieces. Thinking about what would happen if we did cut a figure is one way to tell that two figures aren't equivalent by distortion. Doesn't work very well to tell you that two figures are equivalent, but this kind of argument will tell you when two figures are not equivalent by distortion. Because we can cut the one antenna space alien and get two pieces, and there's nowhere that we can cut the circle and get two pieces, that tells us they have to be different. So again, the book spends a lot of time on this kind of argument, but it's important to realize that cutting it and seeing you get two different things, or you get all one thing, will tell you that two shapes are different, but we couldn't use it to tell that two shapes are the same. It wouldn't be a lecture on topology if I didn't mention that there's a famous running joke among mathematicians. You hear this variations on this constantly at math meetings and so forth whenever you have to deal with topologists. And the joke is that topologists can't tell their donut from their coffee cup. The reason is a donut and a coffee cup are equivalent by distortion. Both have exactly one hole in the middle. If you look at the surface of a donut, it's also called a torus, it has one hole through the middle. A coffee cup is exactly the same. If you took a donut and mashed one side in quite a lot and bent it around so that it made a bowl, then the hole would become the handle for the coffee cup. So the hole in the middle of the donut and the handle on the coffee cup would be the same, and the donut and the coffee cup would be equivalent by distortion.